In the notes, we talked a lot about operators and symmetry and common eigenfunctions. So just to make sure you understand very well what we mentioned there, consider the following statement. So say you have a system, which is described by a certain operator theta, and that system also has a symmetry, and that symmetry is described by a second operator O. Is it then the case that automatically, as soon as you have an eigenfunction of one operator, that same function is also an eigenfunction of the second operator? So pause the video and think very carefully about how this statement is worded, and then try to determine if this statement is true or false. What we actually said in the course notes is subtly different, because there we said that as soon as your system theta has a certain symmetry described by the operator O, that in that case it is possible to construct eigenfunctions which are shared between the two operators. We never said that any of the operators, any of the eigenfunctions of one operator will also be an eigenfunction of the second operator. And that actually makes a lot of sense. Let's focus, for example, on the example where O is the operator describing inversion symmetry. So an eigenfunction of that operator would be any even function or any odd function. And obviously, it's not because you just have an arbitrary even function or an arbitrary odd function, which would be an eigenfunction of O, that automatically such an arbitrary even or odd function would also satisfy Maxwell's equations and therefore be an eigenfunction of the theta operator. That obviously is nonsense. But also the other way around, it's not because you have a function which is a solution to Maxwell's equations and therefore an eigenfunction of the theta operator, that then automatically in that case, that function should be either even or odd. Also, that is not the case. That's a little bit more subtle. And that happens, for example, if you're dealing with degeneracy. So say you have two solutions to Maxwell's equations, so two eigenfunctions of the theta operator with the same eigenvalue. So let's say you have theta h1 is omega squared mu h1, and then you have a second but different solution, a degenerate solution, which has the same eigenvalue. Let's now also assume that the first one is an even function. So if you operate with OI, the inversion operator, on H1, you get back H1. But then for H2, you have -1 as an eigenvalue here. So let's look at this particular case here. And let's now construct a new function f, which is just H1 plus H2. And let's try and figure out if f is an eigenfunction either of theta or of O sub I. So let's see what happens. First of all, when we take that function and we have our operator theta operating upon that function, it's a nice linear operator. So that's just going to be theta operating upon H1 plus theta operating upon H2. And that's going to be omega squared mu H1 because of what we said upstairs there. And then also omega squared mu H2. And thanks to our degeneracy, that is omega squared mu f. So what we have here is that this function f that we constructed is actually also an eigenfunction of the theta operator. The question is that same function now also an eigenfunction of O sub I? Let's see what happens. If we have O sub I of f, again, that's going to be O sub I h1 plus O sub I h2. And now in this case, we have h1. So this is what we have had up here, right? But then when we have h2, that becomes minus h2 in that particular case. Now here we have something very different. This is not equal to some sort of constant times h1 plus h2. So in this particular case, the function that we constructed is not an eigenvalue of that second operator. So be very careful about that statement. As soon as a system has a certain symmetry, this means that it is possible to construct a common set of eigenfunctions. It does not mean that as soon as you have an eigenfunction of one operator, it will also automatically be an eigenfunction of the other operator.